Today we're going to talk about solving systems of linear inequalities. We've been talking about systems of equations, but now we're going to discuss what we do when we have a system of two or more inequalities. So a system of linear inequalities is a set of two or more linear inequalities. An example might look like this. You have the y is less than x plus 2, and you also have y is greater than or equal to x minus 1. It's very similar to when we saw the systems of equations. Obviously, we see the inequality symbols there. So just like when we had the solution for a system of equations being the intersection point or points that are shared in both equations, the same thing is true here. So a solution to a system of linear inequalities is an ordered pair that is a solution of each inequality in the system. So we're looking for points that are solutions to all of the inequalities in the system. So here are the steps. So number one, you're going to graph each inequality on the same coordinate plane, just like we've done. So a couple of reminders on how we do that. We use standard form or slope-intercept form to draw our boundaries. Remember that a dashed line is used for the less than or the greater than boundaries, meaning that the points actually on the boundary are not solutions. And the solid line is used when we have the less than or equal to or greater than or equal to, symbolizing that the lines on the boundary, the points on the boundary are indeed solutions as well. So what we're going to do is we're going to test a point on either side of the boundary once we have created that boundary. If it's a solution, we shade that side. If it isn't a solution, we shade the other side. So far this is just a review of how we graph inequalities. We label each graph with the inequality so that we know which one we're talking about when somebody comes and looks at our graph. So what we want to do now is we're going to use different shading. You can use different patterns, you can use different colors. We want to find a way to kind of distinguish the different shadings that we see so that we can keep each inequality separate and clear. Next, what you're going to do is identify the shading areas where all graphs overlap. You can also refer to this as the intersection area. Remember, it's where we're looking for in our systems points that are in all of the equations or now inequalities of our system. So as we did with the equations, we then are going to test a point that is within our overlapping area to make sure that it works in all of the equations. And we want to make sure that we are testing them in the original inequalities. Because again, if we have to move around some numbers and change some of our equations, we want to make sure we go back to the originals. If the point works in all of the inequalities, we're going to outline the boundaries of the overlapping area, keeping dashed lines still dashed. And just kind of darken or find a way to highlight the solution area so that it is very clear to distinguish it from the rest. So next what we want to do is we want to be able to check solutions, and how do we find out if a solution is indeed an ordered pair to the system? So remember, the solution has to be in all inequalities of the system. So looking at the first one, 3, 5, is that in our inequality? Well, we got to check it. So we do y is less than 2x. When I get the y is greater than or equal to x plus 1. And again, it must work in both. So I just plug in the points. I get 2 times 3. The x goes in as a 3. Is it less than 5? 5 is less than 6. So that is a true statement. 5 is greater than or equal to 3 plus 1. Is 5 greater than or equal to 4? Yes. So what we can answer here is this point, 3, 5, is a solution. So then I move on to the next one. So for the next one, we want to check this point. So again, I'm going to plug in y is greater than or equal to x plus 1, y is less than 2x, and I'm just going to plug in my points. So 0, okay, and when I finish this off, I get 0 is greater than or equal to negative 1. Well, that's true. Over here, though, I get 0 is greater than negative 4. Well, that is not true. And because it is not true for both of our inequalities, then we would have to answer this not a solution. So it's important, again, that we don't just check it with one point and think that it works. We've got to make sure it works in both, or it is not a solution. Here we just have a little bit of a review. Again, we have the dashed line for our boundary. If we have the greater than symbol or the less than symbol, we have the solid line if we have the less than or equal to symbol or the greater than or equal to symbol. And again, that goes with making the boundary part. So now we want to kind of show you what one of these graphs is going to look like. So here we have the system y is less than or equal to 3 and y is greater than x plus 2. So first thing is first, I want to make sure I draw, and you should be using a straight edge even though I am using just freehand because I can't really put a ruler on this or else it would kind of make a mess. So what I'm going to do next is I'm going to put each of these graphs in its own color. I'm going to do the y is less than or equal to 3 in its own color, red. So the y equals 3. Remember, we treat this like it was a regular equation to set the boundary. Our y equals a constant is a nice horizontal line. It is a solid line because of the or equal to part. And our y is less than or equal to 3 is going to look like this. Now when I test a point, for example, I might test 0, 0. I'm going to find that we are shading downward. So then I'm going to move to my second point. So my second equation here is y is greater than x plus 2. Well, this one's in slope-intercept form. So I'm going to go to 0, 2. Use my slope of a 1 to create several points there. Again, this one, though, is a dashed line because I see the greater than only symbol. So this time I'm going to say y is greater than, I don't know why this is making a mess, x plus 2. And the y is greater than, if I was to plug in 0, 0, 0 is not greater than 2. So that just kind of proves to me that I'm going to be shading this way, which is the greater than sign. So we can see how we're going to start making a little bit of a mess here. So what I really need to do is I need to start focusing a little bit more now on this area. So when I look for my overlap area, just notice right through here we have points, and then going right down through here we have points, and that would basically tell us all of these in between. That is our overlapping area. So the last thing I do want to do is I want to kind of prove that this is one of the areas for our solutions, just to prove that this is the right overlapping area. So here's what I'm going to do. I'm going to come across to this point right here. This point is negative 3, 0. So what I want to do is if this is the overlapping area, we're going to test a point. So if I go into my two equations, the first equation would be 0 is less than or equal to 3. Well, that's true. The second point would be 0 is greater than negative 3 plus 2. 0 is greater than negative 1. That is true. So I'm pretty confident that this is the area that we're referring to, and that is basically all we have to show for there. So here we have another system that we're trying to solve with the linear inequalities. This is one that I probably would do a little bit of work on first. I think I'm going to probably move this first one into slope-intercept form. I'm going to get this to be y is less than negative 2x minus 1. I'm then going to change the second one also into slope-intercept form. I think this will end up being better for us to be able to graph to see what this is going to look like. So once I have those pieces, I come over here to my graph, get my y-axis, I have my x-axis, and now I want to graph. So the first one, y is less than negative 2x minus 1. So my y-intercept is there. Go down 2 over 1, down 2 over 1 using my slope. I would have a nice dashed line going through here. And it's saying less than. So if I test 0, 0, I would have 0 is less than negative 1, which is not true. So that would convince me to shade downward. Then I move on to my second equation. Well, this one's y-intercept is at 3. Again, I'm going to come down 2 and forward 1, down 2 and forward 1. Also, dash line, because we don't have an or equal to part. If I was to test 0, 0 on this equation, 0 would not be greater than 3. So again, I would shade away the other way. So one of the first things you might have noticed here is that we have parallel lines for our boundaries. However, I don't want you to think that as soon as you have parallel lines there was no solutions like we had in the systems of equations. You still have to finish the shading. However, in this case there is no overlapping shading areas, so we can finish this by saying there are no real solutions. There are no overlapping areas where these points are in common. Okay, so on this next example, what we're looking to do is we are going to be trying to write our own equations. So we're given the graph, now we got to figure out what does the system look like. So I think what I'll first focus on is this boundary right here. So we see that it's dashed, so we can certainly tell that it's a less than or a greater than. We have a y-intercept of a 0, and I can see a slope of an up 1 over 1 or 1 for how my points are changing. So the y-intercept is 0, my slope is a 1. So slope-intercept form is probably the best choice. So I'm going to say y equals 1x plus 0, which means y equals x. Because we have a dashed line, there's no equal to part of it. And if I think about my shading, I'm going to be shading downward. So it's going to be y is less than x. On my next one, if I focus on the information for this boundary, we are having a y-intercept at negative 2. We have a slope of a 0. I have 0 rise, and the run doesn't matter at that point. But I also know it's a horizontal line, so that's kind of helpful there. We also know how to write the horizontal equations. Y equals where it crosses. So we know that we have something at a negative 2. Because we have a solid line, we know that it is a or equal to graph. And again, if I was to test some points, we'd be shading upwards. So to shade upwards, we need to get a greater than or equal to negative 2. So my overall system is going to be y is less than x, and y is greater than or equal to negative 2. And that is how you would write that system from the graph. So here we have a real-life application we want to look at. We are talking about spending our time at the number of hours at the beach and the mall. We're going to have several different ones that we want to kind of really zero in on, see what we can look like. And again, we're going to make sure that we keep things nice and neat with 3 different equations. So a couple of things. We first want to read through our information. You have at most 8 hours at the mall and beach total. So we want to think about that phrase, at most, and what does that mean. We want to then look at mall and beach time. You want to spend at least 2 hours at the mall. So again, at least is another inequality phrase. And more than 4 hours at the beach. So we want to first kind of look at writing the system. We want to label or identify or define our variables. So I'm going to call the mall X. And I'm going to call our hours at the beach the Y's. So I want to look at my different systems. So my very first sentence is giving us one inequality. We have at most 8 hours to spend at the mall and the beach total. So what that's basically telling me is that I have X plus Y equals 8. Okay, but because we're talking about at most, remember the phrase at most means 8 is fine or less. So less than or equal to 8. Then when I go on to the second equation, at least 2 hours at the mall. That's in sentence 2. Well, our mall is our X. 2 hours at least means equal to 2 hours or more. So greater than or equal to. And on our last one, we're going to talk about the hours at the beach. Well, our beach hours are Y. More than 4. More than is just simply a greater than sign. So that's where we would get the third of our inequalities. Now, because we are talking about hours at the beach and hours at the mall, I'm just going to focus here on quadrant 1, because we're not really going to have negative. So our X is going to be our mall time in hours. And if I look at my beach hours as my Y's, that'll take care of my X and Y axes. Now, when I start looking at this, I want to think about how am I going to graph this? Well, the first one I'm going to probably just keep in standard form, and I'm going to zero in on my X and my Y intercepts at being 8s. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. So there are my X and my Y intercepts. So we can connect this with a nice solid line because it says or equal to. And you can also notice that we are less than that. So I'm going to pick a point. So what if I spend 0 and 0? That works. That tells me that I'm going to shade downward. Okay? Then I move on to the second one. So my second one talks about X is greater than or equal to 2. So an X equals boundary is going to be straight up and down vertical. It has an or equals to part, so that equation would graph this way, first of all. So that would be our graph, X is equal to 2. And it says greater than, which would tell me that I want to make sure I go this way across as the numbers are getting bigger. And I'm just kind of, I could go over more, I'm trying to keep it as neat as I can. On the third one, now I'm looking at Y is greater than 4. So a Y is going to be a horizontal line. This time it is going to be a dashed line, so it would look like this. That's the Y is equal to 4. But because we are going greater than, I just want you to notice how these are now going to be kind of going upwards here. So really, let's go back to seeing what's overlapping on all three areas. Well, really, it's this area right in here. So if I kind of pulled that out, it would be solid line, dashed line. Okay? Right in here into this area. Okay? So that's basically what the graph is going to look like, and I get that it looks a little bit messy. You just do the best you can to try to make it as big as you can and as clear as you can. It also asks us to give a situation where we could spend at these locations. Well, if I'm looking at the graph, it appears to be that the point 3, 5 is in my overlapping area, which would be 3 hours at the mall, 5 hours at the beach. So I should check that. If I go to my first inequality, X's are 3, Y's are 5, 3 plus 5 is 8. 8 is certainly less than or equal to 8. It works there. On my second inequality, if I plug in a 3, 3 is greater than or equal to 2, that one checks. If I go to my third inequality, 5 is greater than 4, that one checks. So what that is basically telling me is 3 hours at the mall, 5 hours at beach would be a possible situation that would work for all of this. It does not mean it's the only one. There are a whole bunch of different ones. It does not have to be a perfect 3 and 5. It could be 2.5. Anything that fits in that window. So it's just one of the solutions that would work, that would give us an idea of what we could spend at the mall. The biggest thing on these are that you are neat, and you make sure that everything is carefully planned out and you are as neat as possible so that you keep your dashed lines dashed, your solid lines solid. You make sure that your shading doesn't overdo each other and that you can see clearly your overlapping area when you are finished.